Are you actually recording? It is recording. I can see it. Okay. So we're on this page, 8.2. We're finding area between curves. So good news. Even though this is new stuff, it's actually going to be using all of the integral techniques that we've been using. So it's still actually kind of good review for the test that's coming up on Friday.
You keep saying review, but I think we have different definitions.
Finding the area between the square and the circle, that's totally review.
No,
Do it without me.
Not using dx or dy method.
Yeah. I don't know what that is.
We stopped the recording.
Wait, I'm trying to spell that. Got through that part.
So if the square has sides of length 10, the radius of the circle is 5. Find the area between the square and the circle.
What does the bare area of the circle pi r squared? It's Mr. Garrison? Or you just memorized the area? I don't know.
So I guess bad news, you have to remember your geometry.
What is that the dx and dy?
Right now we're reviewing geometry because you're going to have to use it in your integrals. So find the area bound between y equals x squared and x equals 1 and the x-axis using calculus. What does each part of your integral expression represent? So here's my picture. Here's y equals x squared. Here's x equals 1. The area that it's asking us to find is this area under the curve. And we know using calculus, we would be able to find the integral from 0 to 1 of the equation of the expression x squared dx. So what do all of these parts mean? Well, x squared is the height of each tiny rectangle we're finding. Zero to 1 is telling us that we are summing up infinite rectangles between these values. Remember our Riemann sums?
Yeah.
We're doing an infinite sum of rectangles. The height of each rectangle is x squared, and dx is the width of each rectangle.
So can the dx change?
It does change. That's the whole point of our Euler method that we just did. Okay. So now, let's look at this one. We have two different curves. We have y equals x squared and y equals x to the third. Here's y equals x squared, and here's y equals x to the third. And if I wanted to find the area in between these using geometry, how would I figure that out? So geometrically, I'm thinking about the area under the blue curve, and I don't want all of it. I only want the part that is in pink. So if I think then about the area under the pink curve and subtracting them, that's how I can find geometrically those areas. So I want to find the integral from 0 to 1 of x squared dx, which is on top, and I'm going to subtract the integral from 0 to 1 of x to the third, dx, which is on bottom. So it's going to be the top area minus the bottom area, and that will leave me my tiny little sliver. So let's do it. For the blue one, the antiderivative is 1/3 x to the third, and we're going to evaluate from 0 to 1. For the pink one, the antiderivative is 1/4 x to the fourth, and we're going to evaluate that from 0 to 1. We'll plug into both of these and figure out what we get. So we're going to have 1/3 minus 1/4, which equals 1/12. Also, this is the concept that we're learning today, which isn't a big stretch.
That wasn't that hard.
The integral from 0 to 1 of x squared minus x to the third dx equals what we have up above. Oh, I said 12 and it didn't write. My mistake. It's not that bad. So let's all take a deep breath and try to put on our big kid pants and get it together. Okay. So now this, it gets a little interesting. Could we find the area using horizontal rectangles instead of vertical rectangles? Horizontal rectangles meaning our slices are going to go this way. If our slices are going this way, our bigger value is the this y, and our smaller value is this one. And I actually would need to think of both of these in terms of y instead of, I'm subtracting my x values. So I need to get it in terms of y instead of x. Okay, so in this case, x equals y to the 1/2. And this one, x equals y to the 1/3. So when I think about this in terms of my y values, my area this way is the integral as y goes 0 to 1 of y to the 1/3 minus y to the 1/2. And I'm taking this with respect to y instead of x. Alyssa, I saw you had a question.
If you're using horizontal rectangles, do you always have to make it equal to x instead of y?
Yeah, you're swapping your x and your y
So
back.
if they say horizontal rectangles, that's kind of like your cue to switch.
Yep. So we're going to start switching back and forth between whether we're doing horizontals and verticals. And you will make that adjustment based on what's easier to do and the information that's given.
It doesn't matter if they're together or separate, right?
What do you mean?
Like
If I did 2 integrals or if I do 1 integral? Like this? It doesn't matter if it's this or this? Correct. They are equal. Okay, so let's do our antiderivative. So we have 3/4 y to the 4/3 minus 2/3 y to the 3/2. Whole thing's going to be evaluated from 0 to 1.
Lie down.
So 3/4, 9/12 minus 2/3, 8/12 is 1/12. Same answer. Thank goodness, because they should be equivalent, right? Right, so here's what we need to understand about these two problems. If both of these problems gave us the same answer and one way was easier than the other, you as a math student have the choice, unless you're told do it this way, you have the choice of the easier of the two techniques. This one, X's were easier, but that's not always the case. So pay attention and figure out which one's going to work better for you. Okay, so let's look at this next one. We're going to consider the region bound by y equals 4x squared, y equals x squared, and x equals 1. So first thing, let's draw a little sketch. So it's two parabolas. And this is where x equals 1. This one, the point is at 1 comma 4, and this point is at 1 comma 1. If I'm thinking about this using my vertical rectangles, I'm subtracting my y's. This top green y minus the bottom blue y, and my integral is going to go from 0 to 1. My top y, 4x squared, minus my bottom y, x squared, the whole thing, dx. I'm going to set up my second problem before I do my integral. So same picture. Sorry, that's kind of sloppy. This is 1 comma 4, and this one is 1 comma 1. If we're doing horizontal, this is a little funky. Do you see how there's two different chunks? For this section, I'm doing x equals 1 minus my upper curve where y is, stand by, y equals 4x squared. Quick, solve it for x. X equals 1/4 y square root. It's square root of y all over 2, or 1/2 squared y. But that area only goes for y values that go from 1 to 4, right? From here to here, y's are 1 to 4. The other area that I'm looking at, this section right here, I'm doing my curve, y equals x squared. So this integral, I'm going to have, we're not subtracting 1, we're doing 1 minus, here, let me finish what I'm writing and then I'll go back to the picture. And this one is this pink area. The y values are going from this point 0, 0 to this point 1 comma 1. So this is from 0 to 1 dy. Okay, let me point at some things. I'm taking slices like this. Okay, so the first set of slices, I'm doing the right side minus the left side. The right side is the square root of y. The left side is the square root of y over 2 because it's this equation minus this equation. Are you okay with the pink slices?
Yeah.
Okay, for the orange slices, what is the right side? What is the boundary?
1.
So that's why I'm doing 1 minus. So in this case, which one was easier? The top one. It's not always going to be that way. All right, so let's do our integral here. We end up with 4/3 x to the third minus 1/3. Oh, I should probably have simplified that, huh? X to the third, evaluated from 0 to 1. I end up with 2/3. Wait. Yes. Yes. Not 2/3. 4 minus 1 does not equal 2. Okay, so theoretically, if we've done all this craziness correctly, we would also get that same value. So let's do it. This integral, we end up with y minus 1/2 y to the 3/2 times 2/3. This one's getting evaluated from 1 to 4. For this one, I end up with y to the 3/2 times 2/3. Oh, do we want to simplify first? We could have simplified this and said this is 1/2 y to the 1/2.
Yeah.
Okay, so then we have 1/2 times 2/3 y to the 2/3. This one's being evaluated from 0 to 1.
Question, where does the 2/3 come from?
Because 1/2, oh, it's not 2/3, it's 3/2. I was using the other 2/3. Thank you for correcting me. Okay, so let's evaluate this. We end up with 4 minus, all that's 1. So 4 minus, square root of 4 is 2, 2 to the 3rd is 8. We end up with 8/3. Minus, plug in 1. 1 minus 1/3. Plus, orange 1. It's 2/2 cancels. We plug in 1. We end up with 1/3. Four minus 1 is 3. Negative 8/3 plus 1/3 is negative 7/3. Plus 1/3 is negative 6/3. And 3 minus 2 is 1. Yay, thank goodness it worked.
Why did we do it this way?
To learn the process.
Miss O'Connor,
Yes.
are we always multiplying when we're doing horizontal? Or are we adding when we're doing horizontal and subtracting when we're doing vertical?
I'm not going to answer your question. I'm going to ask you something different. Why did I add 2 integrals in this problem?
Because you have a pink and an orange part.
So I have different equations marking off my boundaries. These 2 equations are not the same as these 2 equations. So this addition was because I was finding a subtraction between 2 different values here and 2 different values here. So that's why I had to separate it into 2 integrals. It's the same thing as if I gave you an absolute value and I asked find this area under the curve. You would have to split that into 2 integrals and add those 2 integrals together. You couldn't do it as a single integral.
Yeah, but why from 1?
This one, I was able to do it in one chunk because there's no split. It doesn't have that cusp point where it changes which boundary I'm looking at.
But why do we have that in the second one?
Because I'm looking at my rectangles getting sliced this way instead of looking at my rectangles getting sliced this way.
Okay.
Sit with that for a moment. Once we do more, it might start to make more sense. Okay, so write and evaluate an integral expression that will find the area bound between y equals sine x and y equals cosine x over the interval from 0 to 2 pi. Okay, here we go. Let's draw a very good graph. Here's 2 pi. Here's pi. This is 1, and this is -1. I'm going to do sine in red. Sine starts at 0, 0, goes up to the top of the hill, down to the middle, down to the bottom, back up here. Make sure that it is not pointy. Make sure that it is curvy, because otherwise you're going to have a hard time seeing what the picture really looks like. For cosine, we start up here. We come down to the bottom, back up to the middle, and up to the top. Cosine looks like this. If I am asking you for the area between these, I am asking for this area between the two curves. And we should recognize that we are also going to have the boundary of here, 2 pi. That's as far as we're going. So here's the problem. Which curve is on top? It switches. So I'm going to have to split this up into 3 different chunks. I'm going to have it switching 3 different places, okay? And for the sake of time, I'm going to have one more added instruction. Round to 3 decimal places. So we're going to set it up, and then we'll evaluate it. We'll use Desmos to evaluate it, okay? Okay, so here's our setup. I'm going to be using x's as my variable, and I'm going to integrate over the interval from 0 to 2 pi. However, I need to know where I'm switching values. So where are sine and cosine equal to each other? When x equals pi fourths. And then, so this is pi, and the next one is going to be 5 pi fourths. So as I'm splitting up my integral, that's how I'm going to split it. So I'm going from 0 to pi fourths, and I have cosine on top, so cosine minus sine dx, plus my second area. This one goes from pi fourths to 5 pi fourths. And that one, sine is on top, so sine minus of x minus cosine of x. And then my third area goes from 5 pi fourths to 2 pi. And this one I'm doing cosine of x minus sine of x. Oh, I forgot all my dx's. Oh, heavens. There's an alternate way to think about this instead of looking at it in 3 integrals. What's the difference between the area of sine minus cosine and the area of cosine minus sine in this middle chunk? One's negative and one's positive, right? So the alternate way to think about this is we could take the integral from 0 to 2 pi of the absolute value of sine x minus cosine x dx. And that's what I'm going to put into Desmos. So grab Desmos.
Why did you pick sine x to be the first one and cosine to be the second?
I would get the same answer either way I do it. So arbitrary.
It doesn't matter. Like you could do that.
I could have done it the other way. And some people might argue that it makes more sense the other way because you have more of these expressions have cosine on the top, right? Have cosine first. Okay, so let's find my absolute value. Come on. Oh, absolute value right there. Cosine or sine of x minus cosine of x oh, and I wanted to do this before I started typing, I guess. And I'm going to my calculus section. I wanted to be finding my integral from 0.
Where's the calculus section?
If you hit func,
What?
if you hit func, the func part,
Yeah.
and then it gets mad if you don't put in your dx, and you can get that in the ABCs, so dx. Ta-da! Questions? I think we're ending there. Oh my goodness, I just dropped all the things.